Next presenter, Shamparov or Neymanzadeh. Who is present? You present. Okay, so then usual as promised 20 minutes, but not used too much. Please follow the schedule. So after 15 minutes, I will inform you.
Okay. Okay. Good morning. Good afternoon already, everyone. I'm Viktor Shamparov. I'm a PhD student at Moscow Institute of Physics and Technology, and I also am a software engineer in MCS team. We are working on LCC compiler for C++ and Fortran languages for Elbrus and Spark instruction set architectures. First of all, I'm talking about one category of optimizations about data layout optimizations. Why do we need them? Last autumn, we have measured how much time does processor spend on waiting data. We used Elbrus for C for that. It's a processor with in-order execution and 2 cache levels. And there are near 200 executions of spec CPU tests on spec CPU 2000, 2006, and 2017. And more than half of executions spent more than 10% of time on waiting data. So it's a big field for optimization, and we need to do that. Some time losses, of course, are due to inefficient cache usage. For example, in the down of this slide, we have array of structures, and in the cycle, for each element of this array, we have access only to one field. This is a simple example of unnecessary cache misses because arrays of structures in C are saved as one by one with field val, then field ID for the first element, then field val and field ID for the second element, and so on. So we load into the cache both fields, though we have access to only one of them. So half of cache memory isn't used in such case, and we have too many cache misses. There are many cache usage optimizations that are known right now. For example, for this case, we can peel array of structures into 2 arrays. And this optimization is called structure peeling. But there is one problem among them. We do not have right now unified cache usage analysis, which control all of them. So some may have conflicts. Some optimizations may have conflicts between each other. For example, we can firstly peel this array of structures, and then the other optimization called array merging will using its own heuristic will merge them back into array of structures. Though I haven't seen particularly this case, but some conflicts between optimization can exist. So we need to build this unified solution controlling all data layout optimizations. And for this, we need firstly to analyze cache usage in theory. Secondly, we need to develop a method of solving the problem of minimizing time losses based on cache usage analysis. And then we need to make applicable automatic analysis for the compiler. Because if we will just make theoretical analysis, it will be not enough useful for us. And of course, in addition, we need to implement a set of data layout optimizations. Firstly, those which still do not exist in this compiler. And these data layout optimizations should use analysis results. Because of already mentioned problem of potential conflicts between optimizations, we have a restriction that we have to handle all data structures together. So let's go further to what is known right now. There is set of optimizations, as they are named structure layout optimizations in GCC. They use field reference graph, a graph of accesses to structure fields. For example, on the right, there are accesses to fields from 1st to the 6th. And in this example, the D is how much data is loaded between accesses. This data is on the edges of the FRG. But it's not unified enough for us. Firstly, because it's only for structures. Secondly, because it has independent analysis for each structure. And a little point that is not ideal for us, that edges do not show real cache usage. They show how much data is loaded, and there can be some conflicts between already loaded data, so it will change how we can count number of cache misses. Second approach is done by Fragela and Andrada from University of Coruña. Is based on making and solving probabilistic miss equations, which estimate number of misses. For example, for code Lua, there are two arrays, and we can make an equation, right? For example, how it's shown here, and estimate somehow how many cache misses we will get. For this particular example, we think that in every cache line, we have 4 numbers, 4 elements of array. And this approach has also some problems. First of all, it's only for regular access in loops. So if we have other cases, it's almost not for that. Really, there are some irregular access, for example, when there is when the indexes of one array are in another array, but they are not very wide. So there is a lack of unification for all cases. And secondly, it's only estimated number of misses. So they still need to minimize cache misses. They mentioned that it's possible to use this approach for compiler optimizations, but they didn't show how to solve this. So we propose firstly to look at both these methods and to generalize them, because they both have some problems of generality. So we should generalize FRG analysis as common analysis for all data structures, not only C-style structures or classes. But in the PME, we need to generalize as analysis for regular and random access. So we need to add random access and to merge these cases. So next, we need to choose more suitable method, and we need to choose it with the following criteria. Firstly, the analysis should be accurate enough. So which is more accurate, we will think more suitable for us. And secondly, it should work not very long, because it's same that be made in compiler analysis. So infinite compile time is not our case. And the third part is to solve time losses minimization problem. It's a discrete optimization problem because we have some ways, some data layout optimizations, they are known, and in some articles they are listed. And we need to minimize the results of analysis of how many cache misses we will get. Let's begin with FRG. To generalize FRG, we propose firstly to make full reference graph in the procedure for all data structures, for all objects. This will let us estimate number of cache misses. And for each program object, we need to use an analog of FRG graph, an object reference graph. Nodes of in each ORG are a subset of full reference graph. Firstly. Secondly, we noted that in FRG there was not an ideal data on the edges. So in ORG edges, we need to keep probability of awaiting particular cache line between accesses to object. And this probability can be counted by full reference graph. To count these probabilities, we need to know possible memory regions for each pointer. So we need to use pointer analysis and some special profile that collects sizes of memory areas. We can estimate them statically, but it will be not good. It will decrease the accuracy. So next, PME analysis generalizing. For this, we need to develop probabilistic miss equations for random access and to combine already known regular case and developed random case. And also we need to know the same information. which point where points, and how big is each memory area. As for random access, we developed a model with cache states and cache transformation operators. Firstly, we choose cache state as matrix of probabilities of having number of cache lines for each memory area. So, for example, there are two tables here, two matrices, where number of cache lines is from 0 to size of cache. And this is for each memory area from 1 to 3. In this example, we see that A1 is out of cache fully. There is no lines of A1 memory area in cache. And almost all cache is with A2 memory, and maybe one cache line is from A3. And for every code operation and for every code block, we can make a transformation operator, which changes for this operation or block in the cache state. For example, here operation is read from area A1. So one line for area A1 is loaded into cache, and maybe a line from A2 or A3 is evicted from the cache. Then we looked at which transformations are possible for one operation. For example, we see that for one operation, working with some data, we can load new line into cache. We can evict one line from the cache when, for example, it is read.
3 minutes for concluding the question.
Okay. It's almost the last. We can evict one line when the access is to another area, or conflict between lines of one memory areas, or we do nothing. So we make corresponding operator for cache states, and see that transformation operator can be written as a sum of element-wise products of these simple operations of moving up and down, and matrices of coefficients corresponding to which area memory is accessed in this operation. So, as a conclusion, somehow, we can say that firstly, many data layout optimizations are already implemented in our compiler, mostly not by me or not by us as a command who works on this project, but already secondly, we created PME for random access, and we are now unifying it with existing PME for regular access. And also, we are now generalizing FRG approach. So that's all what I wanted to say. Thank you very much. I'm ready for answering the questions.
Please, are there any questions?
No. Actually, I have a question. So probably I missed something. So what's in particular your contribution? You observed two classes of methods. One is field reference graph, and the second one is probabilistic misequations. So did you compare them could you say that one of them is better than another, or you want to use them together? So what is your idea?
My idea is to generalize both and compare them. Compare and choose one which is better. Right now, we don't know which is better, so I think we need to look at them both.
And why do you need generalization?
Because we need to unify this analysis for all known optimizations data layout. For example, FRG is only for structures. So it's used only for 3 optimizations in GCC. They are structure splitting, structure peeling, and field regrouping, as I remember the name. But PME is almost not used in industrial compilers. It's an academic idea, what was proposed by Fragile and Andrada. They showed that it is possible to use, but right now, as I know, they are not used, and firstly. And secondly, they are not common enough because there is case of random access. For example, we can have access in a cycle, in loop, to a list, a standard list, maybe double linked or single linked. And it is, in fact, a random access to all heap. So this case is not handled by PME right now. So we need to do something like that, which I showed. And later, and then unify already known PME by them, and this new PME by us.
Okay, so idea is to unify both approaches, then compare them, and then choose one of them. Which one is better? Or
yeah, you're right now.
Yes. So because previously I thought that you want to generalize them, to combine them and produce some other approach.
Really, maybe it will be done as you say, because maybe we will see that they both that it is possible to make some more general and to some common with them and take advantages from both of them. For example, maybe use the graphs which I mentioned, and I don't know. And for each edge to estimate cache misses or probabilities like PMEs. Maybe. Right now I don't know because it's research in progress.
Okay, thank you.
So thank you. I was not so strict when questions were asked, because we actually have room for due to absent presentation. But I ask next presenters also follow 15-17 minutes, and then we shall see. So next presentation is by who will be Balashov, Grigoriev, I think, who will present?
Yes, I will present. Just a second. Do you see my screen?
We see that it is, now we see your screen. It is not full screen. I see that Ilya Balashov will present empirical study of partial evaluation of matrix and string algorithms. Please.
That's right. Hello, my name is Ilya Balashov, and in this report, it will be an honor for me to tell you about our research work named Empirical Study of Partial Evaluation of Matrix and String Algorithms. To begin with, I should mention that many of huge programs or libraries have some main whole parts which are always under heavy load or on which a lot of other paths. For example, it could be some matrix multiplication algorithm for linear algebra libraries, or pattern matching or regular expression matching algorithms in programs working on strings. So if you are able to speed up with core parts, then we'll be able to speed up the whole big program. However, it is usually very difficult for an industrial programmer to write well-optimized code while keeping with tight time frames or maybe budget frames. Wherefore, there are need for some helper tools or methods that could help programmer to write easier, faster, and more smaller codes. So-called partial relation is, in our opinion, one of such methods. In this report, I will briefly cover the background of the work, the design of the experiments, some notes on implementation details, and of course, a review of the results, and an insight of related research and on our future work. Now, partial relation. Partial relation, which is also known as specialization, is a method of program transformation. It's performed by a tool named partial relator or specializer. Partial relation allows to use some static input data of the program, which could also be considered as a set of restrictions on the program, for a new program generation, which is doing exactly the same thing, but the new program could have changed its properties. For example, it may be faster, smaller, or easier than the previous program. It should also be mentioned that partial relation is also applied for compiler generation with so-called Fittermore projections. For our experiments, we chose NDSL framework, which was developed in Sarah University, and the framework allows a programmer creating applied libraries with the use of partial relation in special domain-specific languages named Impala and Attic. NDSL was previously used in several areas by several research groups, and we received pretty good results in image processing experiments, bioinformatics experience, ray tracing experiments with partial relation. So we want to continue the work with this instrument. Before setting exact goals and research questions of our study, we should choose some algorithms which in theory could be successfully partially related using an abstract great quality tool. We chose two groups of the data. First group is matrix algorithms, matrix multiplication and conic tensor product. These algorithms were chosen because we have some previous research results which were performed in 2020 by different researchers, which shows that partial relation of matrix algorithms or maybe ref algorithms in the form of matrices could be partially related very good. And the second group of algorithms are string processing algorithms, pattern matching, and regular expression matching in matrix form. They were chosen because it's more traditional algorithms to experiment with in partial relation, because the so-called KMP test, which shows how close partially related trivial or substring search algorithm could get to Knuth-Morif-Pratt faster substring search algorithm. And the matrix form was chosen because, as was said, matrix algorithms are specialized very well according to previous research. Moreover, the described algorithms are utilized heavily both in industry and in science. For example, matrix multiplication and conic product algorithms are the main primitives in GraphBus standards, which allows to write some algorithms on graphs using some linear algebra primitives like matrix multiplication. And it's also already mentioned KNP test, and string processing algorithms are heavily used in utilities like grep, which is built in likely the most popular GNU Linux distributors. So our experiments and our optimizations, in our opinion, will have some applied value. Returning to our work, we designed an experiment which covers two main research questions. First one, does partial evaluation benefit string and matrix-based algorithms performance comparing to the basic versions? And the second one, in which degree partially evaluated algorithms code performance get closer to the state-of-art implementations? For the experiments, we chose several data. For matrix algorithms, we chose, to answer the research questions, we chose data sets. First one for matrices. For matrices, we chose Seuss class matrix collection, which is a huge and diverse collection of matrices with a lot of degenerate cases. And the second one is Harrow-Boring matrix collection, which is actually the subset of Seuss class matrix collection, but we should mention it because it's a very big subset. And for algorithms and string, we chose automatically generated strings using some randomizers, traffic dumps from our personal machines. And for regular expressions, we chose regular expressions from the big catalog of regular expressions named regexlib.com. I should mention that we tried to choose the diverse configuration of matrices to cover the most of basic test cases. The more basic test cases, the more different matrices, the more different data we use, the less first validity we have in our experiment. So we also chose a lot of degenerate cases from our data sets to improve the research quality. All the experiments were set up on a stand with the following specs. We use Intel quad-core processor, central processing unit, and 16 gigabytes of memory. ND7 power programming language was used for both evaluated and not evaluated program version implementation. For receiving numbers, we utilized a Google benchmark because it not only allows to measure execution times, but it also provides some statistics, for example, measurement errors. I should say that we were not able to place all the results on the slides, so only interesting one, in our opinion, of course, will be shown. Firstly, matrices. We got 10 times speed up in average for the most of cases, both in tensor product algorithm and the matrix multiplication algorithms. However, there were some degenerate cases. For example, for matrices with elements concentrated near the main diagonal, like Ken 256x multiplied by I3 matrix, and FS 1831 multiplied by I3 matrix in Konica product experiment. This experiment was actually not a great deal because partial relation could not produce more efficient code for loops with very limited number of iterations. The same behavior was noticed for matrices with the high symmetry over the main diagonal. Secondly, the strings. We also got significant speed up compared to non-evaluated version of the code. In details, we got 5 times in average for pattern matching algorithm and 10 times in average for regular expressions. It's interesting that on some, as I could say, convenient cases, partially evaluated version outperforms the usual one in up to 2 orders. talking about state-of-art implementation, the second research question of our study, we chose SUSE library as a state-of-art implementation for matrix multiplication and the Konica product, because this library contains very fast handwritten implementation of these algorithms. So and the GraalBus community considers SUSE library as the state-of-art implementation of their standards, which highly uses matrix multiplication algorithms. Considering the results, partially related Konica product outperforms SUSE GraalBus implementation on all tested cases from 10% and up to 20 times. Even so, matrix multiplication loses GraalBus 5 times on average. It could be some questions on it, but the result could be explained by the usage of the fast handwritten matrix multiplication algorithm, nearly fastest one of the available, and the complexity of the algorithm used in SUSE tends to the minimum possible at the current time. I think nearly every applied partial relator is just not powerful enough for such an optimization, which was performed by the mathematicians. So we think it's a good result for a semi-automatic tool, taking in consideration 10 times win against non-specialized version. The last one, partially related, sync algorithms outperforms the tools from grep family, which are built in like every popular GNU Linux distributive. We got up to 3 orders execution speed up in all cases. So we can consider partial relation a very powerful technique for sync algorithm implementation and optimization. And moreover, NDSL partial relation performed in so-called KMP tests very well. I should remind that KMP test, it's how close partial relation could get with trivial substance search algorithm to Knuth-Moyer-Pratt tests. We did not actually measure how close to the Knuth-Moyer-Pratt algorithm, but we should say that it optimized substance search algorithm very good, very heavily. So we think the KMP test is in some way passed, very abstract way. To sum up in our experiment, in our empirical study, we got 10% to 100 times speed up for nearly all tested algorithms in average, comparing to non-partially related one. And considering comparison with state-of-art implementation, we got 2 to 5 times and up to 3 orders win by time in comparison with egrep family. We got nearly 10 times for tensor products against SUSE implementation, but SUSE won 5 times against partially related code of matrix multiplication algorithm. But we, however, consider it's a very good result for an semi-automatic optimization because we still won up to 10 times comparing to non-evaluated code. And also, I should say that the code was optimized on compile time. So if we use partial relation, we have no need for a heavy library like SUSE. So in applied usage, it could be even better. At the end, I should cover some related and future work on the topic. In previous years, there were some interesting results considering ray tracing, bioinformatics tasks, and image processing tasks in partial relation performed by the NDSL team with the usage of their own instrument. Also, the study on Viterbi algorithm specialization performed by Ivan Tulyandin and to be appeared in proceedings of SEIM conference of this year. And also there's interesting results of specialization of CUDA codes, also an empirical one performed by Alexey Turin in the Principles of Programming Language workshop presented previous year. As for the future work, we have a wide set of directions for the future. It's possible to partially relate more complex algorithms when we chose them. It's also possible to use another tools in languages like NEDSL Arctic language, which supports parametric polymorphism. And it's also an interesting direction to partially relate some code for graphical processes. That's all. I would be pleased to answer your questions.
Thank you very much for such a nice fit in the time schedule. So I have one question from our Zoom participant, Igor Adamovich. Did you use your own specializer or specializer provided by Impala? It seems that it was not clear enough from the presentation.
We used the specialized provided by Impala. Actually, Impala is built into NDSL. So if we use Impala, we must use their own partial relation tool. So we did not implement it our own.
Thank you. Any more questions? Then I have some, if nobody. My question is rather general. Partial relation was invented almost 40 years ago, and it may be surprising while it is not still in practice. What are your impressions based on your experience of these experiments? What are the difficulties of putting partial relation in practice? I hope you have some particular feeling on fingers.
Yes, I have some feelings. The main difference one of the differences comparing to applied software engineering is the need to think very much to write algorithms which could be partially related in a good way, because we need to direct the partial relator manually to perform good optimizations. For example, in the sum algorithm, like the function, some function and the value, it could not be executed right away. So we need to apply some techniques to partially relate the sum and the number. The second difference is the tooling. So we actually cannot use partial relation in widespread tools, which is used in industry. We need to use in the beginning stage tools, which was developed by some research teams, and they are not stable. They are poorly documented usually. So it's a great difference to industrial programming, where like everything is well documented, very stable, and also in our ways. So I think that is.
Thank you for your opinion. And on the slide which we see on the screen, there is a number. Speed up is from 10% to 100 times. Can you generally express, also according to your just informal feeling, when we can expect 100 times, and when there will be only 10%?
10% is reached in some cases where the data is very not symmetric, the algorithm is have a lot of conditional operators, we need to pass the iterations of loops, and these algorithms and this data have very small amount of places where static data could be used to improve performance. In comparison, 100 times speedup could be reached in algorithms which have a lot of static parts, like loop from some constant to some static data, and on data which have some sequences like symmetry, like concentrating elements near some point. So where partial eraser could get some information from this data and use it as a restriction to the program pressurized process. So where the data and algorithms have some static paths in general.
Yeah, thank you very much. Are there any questions? Seems no. Then thank you very much for presentation. We shall go to next presentation.
Thank you very much.
Talk. The next talk is by Arkhipov. Ivan, are you
Hello.
online?
Yes, I will present my work online.
So Ivan Arkhipov will present a generation of optimal object code. Please start.
Okay, I will begin. Hello, I'm Arkhipov Ivan, and I'll present the generation of optimal object code. C language is standard for low level programming, but it have some disadvantages such as pointer arithmetic or lack of control array borders while accessing array element. That's why at the Department of System Programming of St. Petersburg State University, have become the development of Russian translator of C language. Recently, it has become an industrial project. That's why there is a need for optimizations for concrete platform MIPS. So the goal of this work is to implement the optimizing component in MIPS code generator for Rusi compiler. To achieve this goal, we should analyze popular Rusi analogies, GCC and Clang, create a list of optimizations, implement them, and evaluate results and compare again with the analogies. How we should test analysis? So we choose the test of multiplication matrices. The size of matrices is 200, and we took 1000 times multiplication to measure time. The file with assembly code is converted to an executable file with a modified version of GCC special for Baikal T1 processor, and then this executable file is run on this processor with the time measure. That's the first time measure. Clang is the best, GCC on the second place, and Rusi on the third place. Let's look at inner loop code of Clang. What we see here, first comment is calculating the address of A, E, K. Then we take a value from memory for this and for this. When multiplication and addition, when after this we increment induced variable, Induced variable is a variable that is made before a loop body, not to slice element from array in this loop body. So in loop body we may only add something constant value, but not calculate address every iteration. Then there is branch command and again increment. Here we can see a lot of optimizations, such as optimizing serial branch commands, calculating number of loop repeats, using delay slot. About this I will say a bit later. Induced variables and removing unnecessary inductive variables. But there is a disadvantage. Slice of A, E, K is not optimal. For example, for array B, it is optimal, but for array A, we should calculate, we should spend the command to calculate the address. So let's see GCC in a loop. These doesn't have such disadvantage, so and this is increment also, taken from memory varies, again in increment, and multiplication and addition in one command. So as you can see, in a loop of GCC on two commands less than clang. But why this is slower? It's because of emmet command. There was experiment. What should happen if we take emmet command and put instead of it commands of multiplication and addition, and it's work faster. And after this, we put emmet command in clang code instead of multiplication and addition commands, and it's work slower. Wow, it's very interesting, and I think this may be a thing for further researchers. But we continue. So based on the analysis of GCC and Clang, choose such optimizations as optimizing serial branch commands, calculating the number of loop repeats, and using delay slot. We have several approaches how to do this. For example, it may be based on SSA form. A lot of optimizations may be based on SSA form. It is there are a lot of researches on this theme, but these optimizations is rather difficult to make, because you should make a code generator to a SSA and then code generator from SSA. So there is another approach, such as AST based of optimization. It's easy. Optimization path may put information in AST nodes as attributes, and then code generator use this information. But for these optimizations, there is no need for such information, so they may be implemented just in RUSI code generator. Let's look at them. First optimization is optimizing serial branch commands. Optimization consists in reducing unnecessary unconditioned transitions inside the loop body, and there is no need to additional register, so it may be applied to all cycles. Let's have a look at the example. We have a branch comment in the start of, in the beginning of the loop body, and jump comment in the end. Let's organize, reorganize loop body. We put branch comment before body. Maybe we shouldn't go inside the loop, and branch comment in the end of loop body. Yes, and yes, it works. Matrix multiplication have become working faster. Let's look at another optimization. Before loop body, we might calculate condition and put it in some register, and don't recalculate it every loop iteration, but only compare with this register. It is no, it is not possible for every loop condition, but the opportunity to use this optimization is out of this work. Let's have a look at example. We calculate a condition before loop body and calculate condition every loop iteration.
Мам,
What do this?
послушай,
What we do?
какой у нас классный.
Calculate condition before loop body and save it in a register. And every loop iteration we only make this comment, and that's all. We don't recalculate condition. Yeah, it works, and multiplication matrix multiplication program works faster than previous version. Let's go further. Using delay slot. Delay slot is the slot of the comment that is executed without effects of the previous comment, and it is a feature of pipeline computing. The GCC compiler ranges comments if it is possible, and fills this slot. And if it is not possible, it puts no comment here. So we should make an opportunity for GCC assembler to fill this delay slot. Let's look at the example. Okay, here we have an increment of inductive variable. It uses register S2, and branch comment uses register S2. So GCC can't rearrange these two comments and fill delay slot. So we organize cycle such way. We put increment comment in the beginning of the loop body and change condition and increment value so that calculations in loop body was the same. Okay, and here maybe comment that don't use this and this register, and GCC will be able to rearrange these two comments. And yes, it really works, and that's become work faster. That's the final result. It's Rusi is also rather further from this analogous because there aren't many optimizations in the Rusi compiler. And for further optimizations, there are induced variables and reduction of inductive variable. So in this work was the meta-analysis of GCC Clang. Was made a list of optimization. Now in the architecture of Rusi, optimization are implemented. For each optimization, there were tests for correctness. There also the matrix multiplication test was run with a time measure on Baikal-1 processor, and the results are evaluated and compared to again with the analogous GCC and Clang. That's all. I will be glad to answer your questions.
You finished? The end, yes?
Yes, yes.
Yes, I feel- Are there any questions?
I have one or two. May I?
Yes.
Okay, thank you. My first question is about the testing GC and CLang. Is the code for them written in C or RUC or
It
in
is
which language?
it is written in C, and this may compile with Rusi. So these tests may be compiled and with GCC, with Clang, and with Rusi. So
So RUC is a subset of C, yeah?
yes, yes.
Oh, then the next question is about the RUC project at all, because RUC is a subset of C. Why, firstly, not just use it is as a translator from RUC into maybe LLVM IR or GCC intermediate representation, just to use all optimizations and to add some new into GCC or LLVM.
Code generation to LLM is a parallel project. And code generation to MIPS is one of the branches of this project. And after this, we will compare what is better, code generation to LLVM and optimizing of LLVM, and direct code generation to MIPS assembly. But I think it will be further when these branches will be complete.
Thank you.
I have a question in chat. I will read it. From Artem Kotsenyak, if I don't miss this name. Sorry, maybe I have missed it, but what implementation of mat move was used? Naive direct move or second the matrix was transposed? Do you understand the question?
It's about test of matrix multiplication, about code.
Yes.
I think I will show it in my article directly. Why not? Yeah, that's it. That's this code. Well, that's the test for GCC, Clang, and Rusi.
So this is code written by you?
Yes. Yeah.
Not some standard library?
Yes.
Are there more questions? Then I have a questions. What was the decision why you perform optimizations on the code level rather than AST? Or another side of these questions, why these optimizations were chosen for implementation of code level? Because when I follow your three optimization, then I have an impression that only the third one is indeed of lower level. And for examul, counting a loop seems definitely of IST level. It's independent of computer architecture, and it depends on the expressions of the loop. And the first one is somewhere in between. It seems that the code generator was a bit lazy and didn't analyze carefully enough and produce this not enough good code for loop, for branches in loop. Or I have a bad impression. So you see, two sides. Why this optimization are put on low level and why this is.
Yeah, I understand. I think I thought that there is no need to use additional information and additional forms, and this may be implemented only with flags in some code generator while passing IST3. For example, we reached 4 node. We made a flag to make a calculation of number of loop repeats, and it is made by a code generator. And for the first optimization, we put a flag in obsessing for node, and after this, special branch comments are generated. So that's the way I preferred to make optimizations.
Okay. Are there any more questions? No, then we are on time. So this section come to first. Let's thank our presenter, and this section completes. And I give the leadership of the sections to Nikolai Shilov to chair the next section.